Hello, my amazing students. We're on lesson 10 today in our Saxon Course 3 book, and we're talking about rational numbers and equivalent fractions. And we're going to start with the idea of closure. So here is a group that you're familiar with. It's the whole number group, 0, 1, 2, 3, 4, ... Okay, so we know what the whole numbers are. Now, when we're talking about closure, we're starting to talk about what happens to these numbers when I add, multiply, subtract, and divide. If I add a whole number plus another whole number, will I always stay inside the whole number group? Okay, so let's think of a few. If I added 0 plus 5, I'd get 5, and 5 is in the whole number group. If I add 23 plus 23, I'd get 46, and 46 is a whole number. So the set of whole numbers is closed under addition, means that we will not go outside the group. As long as we add two members that are inside the group, we will stay inside the group. What about multiplication? Whole number times whole number. Will I always be in the whole number group? Well, 0 times any number would be 0, and 1 times any number that I chose would stay in that same group. What about any of the others? If I took something like 2 times 3, I'd get 6. Any whole numbers that I multiplied together, wouldn't they be also whole numbers? They would stay inside this group, because remember, this group is all of the whole numbers all the way up to positive infinity. And yes, we would stay inside the group, wouldn't we? Okay, so we found that the whole number set is closed under addition and multiplication. What about subtraction? If I take any whole number and subtract another whole number, will I always stay inside the whole numbers? That depends on which numbers I choose. If I choose a bigger number minus a smaller number, then I would stay in the whole numbers. But what if I chose 6, take away 7? Both 6 and 7 are whole numbers, but the result when I say 6 minus 7, the difference is -1. -1 is not a whole number. Therefore, the set of whole numbers is not closed under subtraction. What about division? Okay, if I say 8 divided by 4, I get 2, and 2 is a whole number. But if I say 8 divided by 16, both of those are whole numbers, but the result is 1/2. And oh no, 1/2 is not a whole number. So to sum up, the set of whole numbers is closed under addition and multiplication, but is not closed under subtraction and division. So let's go talk about the set of integers. So now we're going to talk about integers, which are positive and negative whole numbers all put together. Now, we think about integers. Are they closed under addition? If I start with one integer and I add another integer, will my sum always be an integer? The answer is yes, because remember, the integers are 0, 1, 2, 3, 4, 5, ... and also include -1, -2, -3, -4, -5, ... So if I add two integers together, I will stay inside the integer group. If I subtract two integers, since negative numbers are also in the integer group, then yes, I would stay inside the integer group. What about if I multiply two integers together? Yes, I stay inside the integer group. But what happens about division? All right, so here I took two integers and I divided them. 1 is an integer and 2 is an integer. When I divide it, though, I get 1/2, which is not an integer. 4 is an integer that is greater than 3, which is also an integer. But 4/3 is not an integer because integers are plus or minus whole numbers. And 4/3 is really 1.33333, and it's in between two whole numbers or two integers. So it is not closed under division. So integers are closed under addition, subtraction, multiplication, but not division. Now we're going to talk about an even bigger set of numbers, the rational numbers. And the rational numbers can be expressed as a ratio of two integers. Now, let's think about rational numbers, and whether they are closed or not closed, and which ones. First of all, the rational numbers include all the integers. They include all the whole numbers and all the counting numbers, because the rule for rational numbers is that you can turn them into a fraction. Can't we turn integers and whole numbers and counting numbers into a fraction simply by putting a division sign and a 1 underneath? We can turn them all into fractions. So all integers, whole numbers, and counting numbers are rational numbers. But in addition, all fractions are also rational numbers, or any numbers that could be written as fractions. So if I had something that was not a fraction but a decimal, like a 1.5, that could be written as a fraction, like 3/2. 3/2 is the same thing as 1.5. Then 1.5 is also a rational number because it could be written as 3/2, which is a fraction. So rational numbers include any number that could be written in a fractional form, even if it doesn't happen to be in a fractional form when you see it. Could it be in a fractional form? Could you express it in a fractional form? Okay, so when we think about how broad the set of rational numbers are, if we add two rational numbers together, we stay inside the rational number group. If we subtract two rational numbers, we stay in the rational number group. Remember, rational numbers are fractions made up of all the integers, so they could be plus or minus. Times a rational number times another rational number. If I multiply a fraction times a fraction, don't I end up with a fraction? I do. If I divide a fraction by a fraction, remember when I divide two fractions, don't I just flip the second fraction and multiply? So division of two fractions is the same as multiplication of two fractions. I'm going to stay inside the rational number group. The only tricky thing is that we never ever divide by 0, because division by 0 is not defined. And that's very important for us to understand. I'm going to draw you a picture of that, so maybe you will never forget it. Okay, I just put some pizzas up here. If I had 4 people and I was going to share a pizza among 4 people, I would divide the pizza into 4 equal pieces. I would do this and this. Okay, can you see how the pizza is divided into 4 equal parts? It makes sense, doesn't it? Okay, suppose I only had 3 people and I wanted everybody to have the same amount. I would do something like that, and I could divide the pizza into 3 equal parts. I could divide the pizza into 2 equal parts, and everybody's getting more pizza every time. So 2 equal parts, that makes sense. If I am the only one eating pizza, then do I have to divide it at all? Okay, so one pizza, one person, that person gets the whole piece of pizza. But I could say that one pizza divided by one person is going to be one whole pizza. Okay, so division by one always gives us just what we started with. Okay, but what if I say I want to divide a pizza among 0 people? Does that even make any sense at all? It doesn't. Okay, so division by 0 is undefined. And we want to make sure that we never ever divide by 0 because it is not defined in the concept of division. Therefore, don't do it. Just don't do it. Okay, so here's our first example. We have 3 numbers, -3, 2, and 3/4, that we need to categorize as whole numbers, integers, or rational numbers. And we have to write down all that apply for each one. Okay, so -3 is not a whole number because whole numbers are 0, 1, 2, 3, 4, only positives in 0. -3 is an integer, so we'll write integer. We'll abbreviate it. -3 is a rational number because -3 divided by 1 is a fraction, and all fractions are rational numbers. Therefore, I'm going to say it is an integer and a rational number, and 1, 2, 3, -3 would go right here on my number line. Now, what about 2? 2 is a whole number. Okay, so we'll say 2 is whole. We'll just put WH for whole. 2 is an integer. All whole numbers are also integers. So we'll say integer. And all integers are also rational numbers because all I have to do is put a 1 underneath any integer and it is a fraction. So we will also put rational. Okay, 3/4 is a fraction, but it's not a whole number and it's not an integer. Remember, integers are plus or minus whole numbers, but 3/4 is a rational number. Okay, we forgot to put 2 on here, so let's put 2 on our number line. And 3/4 is less than 1 but greater than 0. So we'll put 3/4 about here on our number line. So now I'm going to show you some cool pictures to relate all of this together. Okay, so this picture is actually in the middle of page 61 for you in your book. But notice that in the innermost is my whole numbers. Now there's actually one inside the whole numbers. We could make another one even smaller. We'll do this, whole. And then inside here, we're going to put natural. Because remember, the natural numbers and the counting numbers are the same. So the natural numbers or the counting numbers belong inside the whole numbers because the whole numbers include 0. But the counting or natural numbers include 1, 2, 3, 4, 5. So 1, 2, 3, 4, 5 is included in 0, 1, 2, 3, 4, 5, isn't it? Okay, and then the whole numbers are included inside the integers because the integers are positive and negative whole numbers. And then the integers and everything inside here are included in the rational numbers, which includes the natural numbers, the whole numbers, the integers, and everything that can be written as a fraction. That's a lot of numbers. Now, fractions, remember, have a numerator and a denominator. And here's a simple fraction, about as simple as we can get. And it means 1/2 means one part out of two equal parts is selected. So here's a picture of 1/2. But notice that if I draw 3 parts out of 6 equal parts, then 3/6 is the same amount, even though it's drawn differently, it's the same amount of pizza as 1/2. So we call those equivalent fractions. And here are 4 fractions that mean exactly the same thing. 4 out of 8 parts, 3 out of 6 parts, 2 out of 4 parts, 1 out of 2 parts. Now, I forgot to say the word equal. 4 out of 8 equal parts, 3 out of 6 equal parts. That's important, okay? So now let's look at the book and see their cool pictures that they have. Okay, so you can see how each one of these is drawn for you in your book. The fractions, 4/8, 3/6, 2/4, and 1/2 are equivalent fractions. We can find equivalent fractions on an inch ruler. Now, I wanted to show you this picture as well because I could not draw anything quite so neatly. Okay, notice how they have the inch divided in. So here's the starting of the inch, and here's the 1 inch. Okay, so if they had that there, that would be, no, I think this would be 0 right here on this line, the way I'm reading it. Okay, so here's a 1/2. And then we cut that in half, and we get a 1/4 right here. So that's 1/4 of an inch, and 1/2 of an inch, and 3/4 of an inch. Okay, now in between each one of those, there are smaller pieces. Okay, so this was a 1/4 right here, but if I cut that in half, I would have 1/8. Okay, if I cut those in half, I would have 1/16. Okay, so our book didn't go down as far as 16, but maybe it did down here. Let's see. No, they didn't go that far. But here we have a little line measure up here. Okay, so we can see that it is 1/2 of an inch. Okay, but let's look at these smaller marks. So 1, 2, 3, 4, and then if we kept on going, wouldn't there be 8? So 4/8. Okay, 1, 2, 3, 4, 5, 6, 7, 8. Right? If we were counting just these big fourths, we'd have 1, 2, 3, 4 fourths in a whole, but that's only 2 of the fourths. Okay, so if we were doing 16ths, each one of these little marks is a 16, and this is 8 out of 16 in a whole inch. Okay, so down here, it says the segment is 1/2 inch long, 2/4 inches long, 4/8 inches long, and 8/16 inches long. There's the 16. The last 3 fractions reduce to 1/2. The first one is already 1/2. We reduce a fraction by removing pairs of factors that have a numerator and denominator have in common. Okay, that the numerator and denominator have in common. For example, we can reduce. Now, this word has gone out of vogue. We usually don't use reduce because we are not changing the size of this fraction at all. Usually this word is replaced with simplify. We can simplify 12/18 by dividing the terms of the fraction by a number that is a factor of both 12 and 18, such as 2 or 3 or 6. So if we want to simplify it down as far as we can, we're going to divide by 6 on the top and 6 on the bottom to get 12 divided by 6 is 2, 18 divided by 6 is 3. So 12/18 is the same as 2/3. So we're going to use, if you can catch Mrs. A, sometimes I still say reduce, but that's generally not what most mathematicians use anymore. They usually say simplify. Okay, So we're going to simplify 12/18 down to 2/3 by dividing by 1. We divided by 1 in the form 6/6. 6/6 is 1. So what our procedure is going to be is we're going to simplify our fractions by dividing both the numerator and the denominator by the greatest common factor. The greatest common factor is often called the GCF, and it is the largest whole number that is a factor of all numbers being considered. So I want you to get these down in your notes because it's going to be very important for you to remember these terms when you're doing your homework. Now, one very easy way to divide by the greatest common factor, which is dealing with what we're studying today or studied last time, which was prime factorization. We're going to simplify 72/108 using prime factorization. So let's take 72, and I'm going to divide out the factor that is prime that I see first, which is a 2. Okay, and 72 divided by 2 is 36. And 36 is also divisible by 2. And then I get 18. And 18 is also divisible by 2. And I get 9, which is divisible by 3 and 3. Okay, so I have prime factored 72, and it is 2 times 2 times 2 times 3 times 3. So let's write it out. 2 times 2 times 2 times 3 times 3. Okay, so now let's take 108, and we're going to prime factor 108 in a very similar manner. I see a 2. Remember, if the last digit is divisible by 2, which means it's even, then the whole number is divisible by 2. So I'm going to divide by 2, and I'm going to get 54. I have a 4 on the end, so it's divisible by 2, and I'm going to get 27. 27 is not even, but it is divisible by 3, leaving 9, and 9 is divisible by 3 times 3. So now I'm going to write the prime factors for 108 up here next to underneath these factors, okay? So 108 is equal to 2 times 2 times 3 times 3 times 3. 2 times 2 times 3 times 3 times 3. Okay, so now I'm going to cancel every factor that is in common between the numerator and the denominator. So 2 cancels 2, and 2 cancels 2, and 3 cancels 3, and 3 cancels 3. So when I look, I have a 2 left in the numerator and a 3 left in the denominator. So isn't 72/108 equivalent to 2/3? Okay, now we just talked about finding equivalent fractions by simplifying and dividing by a form of 1, the same number on the top and the bottom. But now we can also create equivalent fractions by multiplying by a non-simplified form of 1. So if I had 3/3, that's equal to 1, and 6/6, these are both equivalent to 1. But if I multiply by that form of 1, I get a fraction that is no longer in its simplest form. 1/2 is simplified, but 1/2 times 3/3 is 3/6, which is still the same value as 1/2. However, it doesn't look like 1/2. It's not simplified anymore. And 1/2 times 6/6 gives us 6/12, which is the same value, but not in simplified form anymore. Now your book asks a question. What property of multiplication are we using when we multiply a number by 1? Think about it. What we're saying here is that a number times 1 is the same value, even if it doesn't look the same. It's the same value. So we're using A times 1 equals A. Do you remember what that property was called? That's the identity property of multiplication. Okay, so here we're to take 1/2 in example 3, and we're to write it with a denominator of 100. So what we have to think about is what value, we know we have to multiply by 1, but what are we going to use as the form of 1 to get to 100 on the denominator? Starting with 2 times what gives us a 100? Well, we know that's 50. So we also have to multiply the numerator by 50. So 1/2 times 50 over 50 is 50 over 100. Again, same value as 1/2, different numerals, right? So now when we're looking to compare, we've been doing some comparing, but our numerators were the same, weren't they? But now we have a little bit trickier situation. We have to get a common denominator. Okay, so the common denominator that both 3 and 5 would go into would be 15. So let's take this. 2/3 times what gives us something over 15. And then on the other side, we'll put our little compare symbol. 3/5 times something is going to give us something over 15. If we can get both denominators to be 15, then we'll be able to compare the numerators to see which sign is going to go in my compare circle. Okay, so 3 times what is 15? The answer is 5. So we're going to write 5 over 5. 3 times 5 is 15. 2 times 5 is 10. So 2/3 is the same value as 10 over 15. 5 goes into 15 3 times. So this fraction is 3 over 3 in order to be 1. And 3 times 3 is 9. Oh, they're very close. 10/15, 9/15. But since the denominators are the same, we know that 10 is bigger than 9, and we make our symbol go that way. Okay, so now we're moving down here to what are improper fractions. Improper fractions are equal to or greater than 1. So 5/2, 4/4, 10/3, 12/6. Okay, proper fractions, notice that most of these got flipped over except for this one, which was equal to 1. But most of them, we just flipped them over. How can we tell if a fraction is improper or proper? What is the answer to that question? Okay, look at the ones that are improper. What do you notice? They're either equal to 1 or the numerator is bigger than the denominator. Okay, here the numerator is equal to the denominator. So could we say that if the numerator is equal to or greater than the denominator, then we have improper fractions? And proper fractions are those fractions that have a numerator that is definitely smaller than the denominator. That would be a good way to tell, wouldn't it? Okay, so we learned what an improper fraction was, what a proper fraction is. What is a mixed number? It is a whole number and a fraction put together. And if we have a mixed number, it can be expressed as an improper fraction, and vice versa. If we have an improper fraction, it could be expressed as a mixed number. So 2.5, I've drawn 2 wholes and a half. So let's just take part of this off. Okay, and could we express this also as 1, 2, 3, 4, 5 halves? They mean the same thing, don't they? Okay, so here we have an improper fraction that we're turning into a proper fraction here. I mean a mixed number. We're going to turn it into a mixed number. So we have 10 thirds is equal to 3 thirds plus 3 thirds plus 3 thirds. And that would be 9 thirds altogether, plus one more third would give us 10 thirds. So drawing a picture, if I have 10 thirds, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, so this is 3 thirds and 3 thirds and 3 thirds, which are each wholes, and 1 third left over. So 3, 1, 2, 3, and 1 third. Now, that's kind of the long way to do it, but it works. But the short way would be to do what? 10 divided by 3 goes 3 whole times with 1 left over. Okay, so 10 divided by 3 goes 3 whole times. 3 times 3 is 9. We take away, we have 1 left over, so 1 third, 3, and 1 third is our answer. And if we're going backwards, we would say 3 times 3 is 9 plus 1 is 10. 10 thirds is the same as 3 and 1 third. And you have to learn how to do that pretty quickly. Okay, so here we have our last item before we go to our practice problems. 12 divided by 6. Well, 12 divided by 6 we already know is 2. But if we were going to take the longer way to go, we could say, well, I could pull out one set of 6. 6 over 6 plus 6 over 6 gives us 2 wholes, which is 2. Or I could take each one of these pizzas that are divided into 6 pieces, and I could start counting pieces. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12. So let's start on those practice problems. Remember, your practice problems are a required part of your homework, and I'm doing them all for you. So go to your worksheet now. Okay, so practice problem A. Actually, it's A, B, and C that we're doing here. So we're going to tell whether each number is whole, integer, or rational, and we're going to list everything that applies. Okay, so just for this exercise, I'm going to use W for whole, and I for integer, and R for rational, just to make it a little bit less writing. 5 is a whole number. Remember, whole numbers are 0, 1, 2, 3, 4, 5, 6, and so forth. Integers are positive and negative whole numbers. So remember, this group belongs inside the integer group, and the integer group belongs inside the rational numbers. Okay, so since it's a whole number, it's also an integer, and it's also a rational number. So we're going to put whole, integer, and rational number for 5. But what about negative 2? Negative 2 is not a whole number, but it is an integer because the integers are positives and negatives. So it's an integer, which makes it also a rational number. Remember, every integer, all you have to do is put it over 1 and it becomes rational. So we'll put integer and rational. And lastly, negative 2/5. It's a fraction. So it is rational, but it is not an integer and it is not a whole number. So it is only a rational number. And there you have A, B, and C in one fell swoop. Okay, so now we're going to do letter D in our practice problems. And we are going to prime factor 20 and 36 and then cancel the common factors to simplify this fraction down to its lowest terms. So 20 divides by 2, leaving us with 10, and divides by 2 again, leaving us with 5. So we will write 20 as 2 times 2 times 5. 2 times 2 times 5. 36, we're going to divide by 2 to get 18. And divide by 2 again to get 9. But 9 is divisible by 3 and 3. So we're going to have 2 times 2 times 3 times 3. So now we're going to cancel the common factors. And we have a 2 and a 2, and a 2 and a 2. But 5 and 3 have nothing in common between the numerator and denominator. So our fraction is going to simplify to 5. 3 times 3 is 9, and 5/9 is the same value as 20/36. You can check it. 5 needs 4 to get to 20. 5 times 4, so if I multiplied by 4 over 4, 20 over 36, it would go right back there, wouldn't it? So the answer is 5/9. Okay, so the next fraction we're going to simplify is 36 over 108. So 36, we're going to prime factor, and I could start with a 2 or a 3. I'm going to start with 3 this time. I want you to see that I'm going to get the same prime factor I would get either way. So 3 goes into 36 12 times. But 12 is divisible by 2, leaving me with 6, and 6 is divisible by 2, leaving me with 3. So 36 is 2 times 2 times 3 times 3. Notice how I always write my prime factorization, smallest factors to largest factors. Okay, so now let's do 108. And 108 is divisible by 2. Remember, these are always going to be prime numbers that I pull out. And I'm going to have 54, which is also divisible by 2, which is going to leave me 27, which is not divisible by 2, but it's divisible by 3, giving me a 9 and a 3 and a 3. So 2 times 2 times 3 times 3 times 3 goes here. Okay, so now I start to cancel. 2 and 2, 2 and 2, 3 and 3, 3 and 3. I am left with 1 3 in the denominator, so 36 over 108 is equal to 1/3. And guess what? If we multiply by 36 over 36, we get right back to the original number. And now we're ready to do F. Okay, so now we're doing 75 over 100. Now remember that even though I'm doing them for you and I'm factoring them for you, you should still show all of that work on your worksheets because you're supposed to be doing this and learning how to do it. Not me. I'm just doing it with you, not for you. Okay? So 75 over 100, what is it equal to? So let's take 75 and let's prime factor, and we're going to take out a 5. We take out a 5 out of 17. 5 goes in one time with a 25 left. We get a 5, 15. And we're going to divide by a 5 again and get a 3. But remember, when we write our prime factors, it's going to be 3 times 5 times 5 because we start with the lowest number. Okay, so now we're going to do 100 and factor it by a 2, which gives me a 50, and by a 5, which gives me a 10, which is a 2 and a 5. So 100 is 2 times 2 times 5 times 5. Okay, so now 5's cancel, 5's cancel. 3 over 4 is my simplified fraction. And now we're ready for G. Okay, so 3/5, we're trying to get to 4 times. So I'm going to multiply by 1 in the form of 4 over 4. So 5 times 4 gives me 20, which is what I want. 3 times 4 gives me 12. So 3 over 5 is the same as 12/20ths. 3/4 is how many 20ths? Okay, so 20 divided by 4 is 5. So we're going to multiply by 1 in the form of 5 over 5. 4 times 5 is 20. 3 times 5 is 15. So 3/4 is the same as 15/20ths. 1/4 is how many hundredths? Well, 100 divided by 4, remember there are 4 quarters in a dollar? So 100 divided by 4 is 25. So we're going to multiply by a form of 1 that is 25 over 25. 4 times 25 is 100. 1 times 25 is 25. So 25/100ths is the same as 1/4. I'll hold all 3 of those for you for a second. Okay, so this is J in your practice set. So we have 3/5 and 3/4 that we are comparing. Now, we could use what we learned before. Since the numerators are the same, then this pizza is divided into more people. So this is going to be less than, okay? But let's go ahead and do it with our new material, okay? Let's get to a common denominator of 20. Okay, so 5 times 4 is 20, so 3 times 4 is 12. And 4 goes into 25 times, so we're going to multiply this side by 5 over 5 and get 15 over 20. This side was multiplied by 4 times 4, which gave 12 over 20. So now can you see that 12 over 20 is less than 15 over 20. So since we're doing this as part of our homework, let's go ahead and do them this way, seeing as how that was the old way. We were just learning about fractions, but now we're doing bigger stuff. Okay, so we're on, what is this? This one is K. We're on K now. It says, sketch a number line and place these numbers on the number line. Okay, so -1 has got a spot. 3/4 is bigger than 0 but less than 1. So we'll put it right here. Okay, so we'll say that's 3/4. This is -1. 0 is right here. It's got a spot. Okay, 3/2, if I make it a mixed number, is 1.5. So it's going to be right in between 1 and 2. That's 3/2. -1/2 is going to be way over here. It is in between 0 and -1. So it's too far away to draw it. So we'll just label it. -1/2 is right there. Okay, can you see that? So on this one, we're supposed to take 9/4 and turn it into a mixed number. And this one is L. Okay, so I'm going to do it 2 ways. I'm going to do it with pictures. So if we had pizzas divided into fourths, how many pizzas would we fill up? Okay, so we would have 1, 2, 9 pieces, right? 3, 4, 5, 6, 7, 8/4 plus 1 more fourth. We haven't gotten the 9/4 yet, right? Plus 1 more fourth would make 9/4 altogether. So 9/4 is 2 wholes and 1/4 left over. So that's with pictures. Now let's just divide it. 9 divided by 4. 4 goes into 9 2 times, 2 whole times. 2 times 4 is 8 with 1 part left over out of 4 parts. So that's 1/4. 2 1/4 is the answer. Okay, so for M on our practice, it says, what property of multiplication are you using in problems G through I? Now, if you look back at G through I, we were turning, here's G through I right there. We were turning a number into an equivalent fraction with a different denominator. So we were figuring out which form of 1 we needed to multiply. Whenever we multiply by 1, that's the identity property of multiplication. So G through I is using the identity property of multiplication. And the identity property of multiplication says A times 1 is still A. And since we multiplied by 1 in a different form, it didn't look like A, but it still had the value of A. Okay, this is our last practice. It says, give an example to show that the whole numbers are not closed under subtraction. Now remember, whole numbers were closed under addition and multiplication, but not under subtraction or division. So all we have to do is come up with two whole numbers who, when you subtract them, are not, the answer is not in the whole numbers. And that's easy. We're going to take 5, take away 8. If we start with a smaller number and subtract a bigger number, we end up with a negative number, and negative numbers are not in the whole numbers. Now we're going to start your actual written problems, so make sure that you are showing all of this and the next 5 or 6 problems on your little packets. All right, so this is problem number 1 in your practice, in your written practice. Okay, so we're to show that 15 is composite with rectangles. So we know that any number that factors in 2 different ways is composite. So 15 times 1. Now, if that was the only way we could factor 15, that would be prime. But if we have 5 times 3 also, we say, okay, this is composite because there are 2 different ways to factor it. So 15 times 1, wouldn't that just be a long rectangle with 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. I had to make them real skinny, okay? But 15 times 1, or since it's 5 times 3, let's make it 3-story. 3 stories and 5 across. 2, 3, 4, 5. Okay, that's all there is to it. Okay, so factor tree to prime factors of 90. This is problem number 2. It says draw a factor tree for 90. Well, I'm just going to pick out 9 times 10, and then I'm going to factor 9 further into 3 times 3 and 10 further into 2 times 5. So remember, prime factors go least to greatest. So 2 times 3 times 3 times 5 will be the answer to number 2. Okay, so this is number 3 on your written practice set. And we're trying to find the number that has 5 and 3 as factors. It has to have both of them. We can cross off 2 of these right away because remember, if it has a 5 in it, it's either 5 or 0 at the end. That one does not have a 5 or a 0 at the end. That one does not have a 5 or a 0 at the end. Both of these are divisible by 5 because they have a 5 or a 0 at the end. So all we have to do is take each one of these 2 that are left and check to see if 3 goes in. Now remember the 3 rule. I add up all the digits. If the sum is divisible by 3, then the whole number is divisible by 3. 4 plus 2 is 6, plus 5 is 11. 11 is not divisible by 3, therefore 425 is not divisible by 3. We got to hope this one is, right? So 1 plus 6 is 7 plus 5 is 12. 12 is divisible by 3. Therefore, 165 is divisible by 3. It's also divisible by 5. And the answer is D, 165. Okay, 165 is number 4. We're dividing 165 by prime numbers to find its prime factorization. I'm going to start and divide by 5 because I know it has a 5 in it. So 5 goes into 16 3 times with 1, 5, 15 left over. 5 goes into 15 3 times. So 33 times that 5 goes into 165, and 33 is divisible by 3 and 11. Therefore, the prime factors of 165 are 3 times 5 times 11, because I always write them smallest to greatest. This is number 5 and the last one that I'm going to do for you on the video. Okay, remember, we're going to simplify by prime factoring each number. 22 is pretty simple. It divides by 2, leaving an 11. So the factors are 2 times 11, done deal. Okay, now 165, we just did factor it, but let's do it again. It has a 5, and 5 goes in there, 3, carry the 1, 3, 3, and 11. So 3, 5, 11, 3, 5, 11. Okay, so we say the factors, divide by 11, divide by 11. 2 over 15 is the simplified form of 22 over 165. And we have done all of your practice problems, and we have done 5 of your real problems. Hopefully that's enough to get you really clicking along on your work. This is Mrs. A, and may God bless your day.